All right, good afternoon, everyone. Welcome to another video about IB. And today we're going to talk about IB flux and Faraday's law. This is topic 11.1, and it goes well with the Alberta curriculum's unit on electromagnetic induction and Lenz's law, which is in unit B of the Alberta curriculum. So, however, it is usually followed up in the IB curriculum by, well, once you induce the current, which will be an AC current, as one you'll learn after when we talk about Lenz's law. After this, okay, will be an AC current. So naturally, next thing to talk about is power generation, and talking about the transmission of of alternating currents. However, I will not focusing on Lenz's law or too much in this video, and I will also not be talking too much about AC current, the DC current, and transmission, all that. This will focus specifically on the concept of flux and the immediate implication of Faraday's law. However, this video, I am going to use the first bit of this video to go over some questions asked by students of my class this year. It will be edited out in the official version. Maybe I'll leave it in. I don't know. But there are some questions from my class which I didn't quite cover, so I would like to use this video as well to you know what, I'll leave it in to talk about some questions regarding because it's related. It's somewhat related to the concept of electromagnetic induction. So I will be answering those questions. I wonder if possible on YouTube I can split it into two separate videos. So, anywho, let's take a look. So, well, I guess if I cannot edit it out, I will leave the video. I will leave this section in for students in the future to look at, because once again, this is indeed related to the Faraday's law and later Lenz's law as well. Which is once again used to calculate the strength and speed of the law. So recall that if there is a charge that's moving in a constant, okay, unchanged magnetic field, in this case, as you can see, an electron is moving towards the right, then the magnetic field is moving into the page. Using the third hand rule, one can easily determine that the electron will experience a it will experience a force. There we go. We'll experience a force down in this direction. Okay, down in this direction, and cause the electron to accelerate. However, once it's down here, if you continue using your hand rule, you notice the electron experiences a force this way, which causes the electron to go this direction. Eventually, cause the electron to be trapped in a circle. Okay, right. Of course, the force responsible. Okay, the force responsible for this motion, of course, is equal to the magnetic force resulting from observation of the Lorentz force. Okay, which you can predict using the third hand rule. However, it is in circular motion. It is in uniform circular motion, which means F net has a special name, which is the centripetal force. Is equal to Fm. Now we know for moving charge, right? Moving charge, the magnetic force on moving charge, at least, well, the magnitude will be equal for sure. So the magnitude of the charge, of course, is equal to Q times the speed, not velocity. Direction doesn't matter here. Charge of the particle that's moving times the strength of the magnetic field, and that must equal to mv squared. Notice I'm using speed here over, oh, wait, mistake, v squared over the radius. And by relating these two forces together, one can come up with a number of very, very important discoveries, which from which from predicting behaviors of known particles as well as understand properties of unknown particles. In fact, a very similar formula was used by J.J. Thomson, as we'll briefly talk about. J.J. Thomson, the Nobel Prize winner who discovered the electron to determine the charge to mass ratio of said electron. But I'll briefly mention that a little bit later. And of course, a very typical problem would be something like this. Calculate the radius of electron traveling at a speed of 3.60 times 10 to the 4 meters per second perpendicular through the magnetic field. Now, the perpendicular here is actually quite important. Okay, actually quite important because remember that in a magnetic field, only if the particle is moving perpendicular to magnetic field, we experience a force. If particle is not moving perpendicular, it might result in some strange behaviors. So, this is an image here that I found. I'll briefly talk about, briefly reference here. So, remember, only the perpendicular component experiences force. So, if you enter the field parallel, nothing will happen. You do not experience any force. Only if the velocity moving perpendicular experience a force. If you enter any angle, then horizontally you will be moving in uniform motion. So it's just going to be constantly forward, while the vertical direction will experience circular motion, causing it go into a spiral, like as you can see here. So very important that only the perpendicular component, actually experiences a force. You can measure the angle between the direction of movement and the direction of the field, and then you can use cosine, sine, and so on to figure out exactly which component it is, but that's not here or there. That's not our focus right now. Here, our particle is moving perpendicular, so everything's fine. So, we know that I use PP0, PP2 here, but that's the Alberta curriculum notation. I usually use the proper general notation, which is uniform motion here and uniform circular motion here. Alright, so here is calculating the radius of a particle moving perpendicular to radius of an electron moving perpendicular to the magnetic field. So we know that it's going to be in circular motion. So we can even draw a circle here and say the causing to move is Fm, right? It's the electron. So we know centripetal force is equal to the magnetic force, and as we said earlier on last page, mv squared over r is equal to qvb. I'm going to drop the vector arrow because indicating I don't really care about direction right now. Radius is a scalar, so I'm only care about what radius actually is. Alright, you quickly notice that the v, there are v on both sides, so this v actually cancels, so it turns into mv over r equal to qb. Quickly rearrange, you'll find out that r is actually equal to, just a cross multiply, okay, is equal to mv over qb. Okay, mv over qb, and then we are done. Because we have all those values. The mass of the electron is 9.11 times 10 to the negative 31 kilograms. The speed is given to us 33.60 times 10 to the 4 meters per second. The charge of an electron is the famous 1.60 times 10 to the negative 19 coulombs. And the strength of the magnetic field is 4.20 Tesla. You can go in and be careful and check all the units, make sure they all work out, but it definitely does. So I'll quickly plug this into my calculator here. So 9.11 times 10 to the negative 31 kilograms times 3.60 times 10 to the 4 meters per second divided by 1.60 times 10 to the 19 coulombs times 4.20 Tesla. That's a really strong magnetic field. most magnetic field is only like 1 or 2. It's probably strong. Sure, I didn't. Oh, coulombs. And I get an answer of, with 3 sig dig, of 4.88 times 10 to the negative 8 meters. That way small radius. Okay, a very small radius, which is expected. It's an electron. So for electron, that's actually pretty big. Okay, for us, it's very small. And it's something that a detector certainly can detect. There it is. It's a very simple, very straightforward application of magnetic. Well, it's not electromagnetic induction, not quite there yet, but interaction between electric field and magnetic field. Now, a very common application of this is known as a mass spectrometer. This is a very simplified version of a drawing of mass spectrometer. It does get complicated, but essentially the idea is it's something used to determine the mass to charge ratio and other properties of charged particles. Okay, which is often used to identify unknown ions. So you put something in there and you can detect different compositions by adjusting settings. Of course, a lot of them can be done automated. Okay, but how does it work? Well, the key part, of course, is at the very end, the detector. A particle will enter with a certain speed. And then, of course, here circular motion is equal to there's only a magnetic field here. The only field here is a magnetic field. And as we've seen before, this is mv squared. I'm going to skip a step and reduce the v already. And you can quickly see the charge to mass ratio. I can rearrange. It's equal to by dividing the b over and dividing the m over. So I switch b and m basically. Divide b and divide m. So I can get a charge to mass ratio. You can quickly see so you can see that the charge to mass ratio, or mass to charge ratio, I guess, depending on what you like, is equal to the speed of the particle over r times b. Right? So the magnetic field, of course, is controlled, so that's a known value. The radius, which is kind of measured, right? You can just measure that radius. The detector can certainly easily measure. The difficult part, of course, is speed. So where did the speed come from? Right? The speed come from? Well, that speed came from the velocity selector. Only specific speed can get through. How does one achieve that? Well, that's actually also a very ingenious combination of both the electric field and the magnetic field. What happened is, of course, let's suppose this particle is some charge, positive or negative, right? But by design, let's say the top plate is it's expecting to detect a let's see, I'm going to do my hand real quickly here, into the page. So it is expected to detect a negative particle, let's say. So the setting will set the plate to this way, which means the particle here, if it's negative, you experience a electric force upwards. However, if you do your hand rule, you will notice that using your third hand rule, that's the electric field. The magnetic field here, okay, I will slightly color code it. The magnetic field here is into the page. So if you use your hand rule, you'll notice the magnetic force is down. Alright, magnetic force is down. Now, in order for the particle to have the right charge and the right speed, remember the important part is the speed. To have the particle have the right charge and the right speed, right? Those two forces has to be balanced so the particle goes straight through. So we conclude, okay, I color code already, so I'm doing here. Conclude over here, we want the Fe to be the opposite of F, the magnetic force. Specifically, of course, is that the charge of the particle times electric field is equal to, well, the particle experience is equal to QVB. Right? If you look at the magnitude, specifically the magnitude, the direction, of course, determines the charge, right? If a charge is the wrong sign, you'll crash and burn, all right? But in terms of magnitude only, okay, if it's magnitude, those are equal in magnitude. All right, same charge here, so the charge will cancel, right? And if you pay attention to, if you actually want to pay attention to the sign, you know there's a negative there. However, it's not too much of an issue because once again they're negative because they're opposite. The field and the two fields offer the force in two opposite directions. With a quick rearrange, you'll see that V must equal to the ratio, the speed ratio between the electric field and the magnetic field. So those two fields, so we know whatever particle that comes through here, the speed must equal to E over B, the ratio from here. Right? So we know its speed. And there, we can calculate, from there we know its speed. Okay, we don't know its charge. Right? We don't know its charge. We know it has it's negative, for sure. We know it's for sure it's negative. In fact, we know it's negative way before that, of course. But we know the charge in the right sign, and more importantly, it has the right speed. So we can find the charge to mass ratio, and of course, with if you have a list of data, you can say, oh, this is a particle I expect. This particle has the right charge mass, so this particle must be this. We can determine the density of the particle. Now, of course, normally particles are not moving. They're moving randomly, very slowly. So how do we get the particles to move in the first place? And that is, of course, this accelerator. Once again, let's assume we're trying to accelerate a negative charge. Once again, I did say the charge is determined very earlier. They're very easy, which is to put a positive plate here and put a negative plate here. And there's only going to be electric field here. Only, right? Electric field. Then, of course, then the particles can accelerate, and the energy gained, of course, is going to equal to the changing potential energy. So the work done is equal to the work done. So changing EK. It's assuming you can assume it's at rest in the beginning, but let's leave it like this. Okay, it's equal to V times Q, and then let's assume at rest, and a start. At least it's random, so it's on average it's at rest. So we can get 1/2 mv squared is equal to VQ, and you can easily see the speed that will enter here. Hopefully they're the same speed. The speed will enter will be 2VQ over m squared root. Okay, so that's how mass spectrometer in essence, that's how it works. It's, of course, it gets much complicated, right? It has to be able to control the field, and what if you want to work with a positive particle, negative particle. It's more complicated, of course, the real one, but in principle, that's how a mass spectrometer works. And yeah, that's it. That's circular motion. And now we're ready to talk about the Faraday IB stuff. So this is Alberta curriculum and IB. It's in both, of course. And afterwards will be the IB stuff. I just thought of a really lazy way for me to solve this issue, which is just me to end the stream right now and start a new stream, which is a new video. I think I will do that because it's easier for me on the post-production end. So I'm going to end the stream right now, do some light editing. I'm going to start the stream up right away, talking exclusively about IB stuff, so I don't have to worry about cutting into 2 clips and so on and so forth. Alright, so if you are watching, if you don't have any questions, I would end the stream and then just start back up after I finish dealing with this first part. Cool. Alright, see you back shortly.